Okay, so we have a little bit more to discuss with complex numbers. So kind of zoom in a little bit there. First thing I want to look at is higher powers of complex numbers. So I'm going to start by just taking the number I, the imaginary constant, to the power of 1. If you take anything to the power of 1, you just get the number itself. So I to the first power, clearly that would just be I. What if I raise I to the second power? Well, we already know what that is. By definition, I squared is -1. Okay, but what about if we do I cubed? Well, I cubed means I times I times I. Or another way of thinking of it is I squared times one more factor of I. So if I were to multiply I squared by another factor of I, that gets me I cubed. But if I squared is equal to -1, that's the same thing as multiplying -1 by another factor of I. That gives me -I. Okay, what if I multiply I cubed to another factor of I? So as I work my way down this list, I'm just continually multiplying each previous step by another factor of I to the fourth. That's like taking -I, which we had up here, and multiplying it by I one more time. Well, if I multiplied this by I, it would become -I squared. But I squared is -1, so that makes -1, which is +1. Okay. Now, if I continue with this list, this is the step where something kind of interesting happens. If I do I to the 5th power, again, it's multiplying the previous step by one more factor of I, but 1 times I, just like 1 times anything, is itself. And if you notice, I'm back to I again. I'm back to where I started. So if I continued this pattern, I'm just going to see, or sorry, if I continued this list, I to the 6th, I to the 7th, I to the 8th, so on and so forth, all I'm going to end up with is this repeating pattern of I, -1, -I, +1. It's a cyclical pattern. So what this does for us is it makes it so we don't have to manually multiply out high powers of I if we know how to use this pattern. So let me try one where the power of I is very large. Let's say I wanted to evaluate I to the power of 103. Okay. One thing you could do is recognize that this is a repetitive pattern and then multiply I to itself 103 times to see which part of the pattern you land on. But that's excessive. You don't want to do that. You don't want to list 103 different things there. So what would be easier to do is to come up with a way of determining what position in this cycle of 4 this should be in by using division. Here's what I mean. So notice if I did continue this list, I to the 6th, I to the 7th, I to the 8th, I would get -1 here, -I here, +1 here. If you notice, every single time I raise I to a power of 4, or sorry, I to a multiple of 4. So if the power here, the exponent is a multiple of 4, 4, 8, 4 more of these would give me a 12 down here. I get a 1 each time. So now come up to here. I'm going to try and represent this slightly differently. Notice I to the 103rd power is the same thing as I to the 100 times I to the 3rd power. It may not be clear why I chose to split this up this way, but if you just kind of follow along with me for a second, I know that the number 100 is divisible by 4. So one thing I could do to this is write this as I to the 4th to the 25th power times I cubed. What I'm doing is I'm using an exponent property, because if you have a power to a power, these can be multiplied. 4 times 25 gives me 100, bringing me back to this. But I'm sort of, rather than simplifying it, I'm making it look more complicated. The point of that is that I to the 4th, as we know over here, is equal to 1. So this is the same thing as 1 to the 25th power times I cubed. 1 to any power is just 1, and multiplying this by 1 is just going to give me I cubed. So if you notice, what I've done is I've taken this higher power of I, and I've reduced it down to I to a much smaller power, specifically one of these 4 powers here, 1, 2, 3, or 4. So that makes this a lot easier. If I use my list here, I know I cubed is equal to negative I. So this whole thing is equal to negative I. Now that's great, but this process may seem a little bit difficult to start because it's not clear how I chose to split these up. So there actually is a much better way. The key here was to pull out the biggest multiple of 4 from this power 103. But really, that's the same thing as dividing this number by 4. This number here is simply going to be the remainder of that division. To show you what I mean, if I did 103 divided by 4 using long division, 4 goes into 10 twice, and I get 8 here. Subtract to get 2, bring down the 3. 4 goes into 23 5 times. 5 times 4 is 20. Subtract and get 3. My remainder there is 3. Now the 25 shows up right there. The 3 shows up right there. So if you notice, the remainder of this division after dividing my exponent by 4 is the thing that I ultimately am actually raising my I to. This trick will work for any higher power of I. Let's try another one. If I wanted to do I to, let's say, the power of 260. I to the power of 260. Well, let's divide 260 by 4, always by 4, and see what we get. 4 goes into 26 6 times. That gets me 24 here. I subtract to get a 2, bring down my 0. 4 goes into 20 5 times. I subtract and I get 0. Notice here the remainder is 0. You normally don't write remainder 0, but I'm going to write it because I know that this will become the exponent that I need. That remainder tells me that this is the same as I to the power of 0. Now notice I didn't see I to the power of 0 in this list, but if we work backwards, then the number that should have shown up right before this I right here, so if we go to this I, is a 1. I to the 0 should equal 1. And of course it should equal 1 because any non-zero number to the power of 0 is supposed to equal 1. So that tells me that this comes out to just 1. Okay, that's how we handle higher powers of I. Last couple of things I want to look at are algebraic in nature. So the first one is going to be the quadratic formula, which we know from algebra. The quadratic formula involves a square root, that plus or minus b squared minus 4ac. In fact, let's write it. If I'm trying to solve this, ax squared plus bx plus c equals 0, so a quadratic equation equal to 0, then the quadratic formula says that my solutions will be x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Now, if the result of this b squared minus 4ac, we call that expression under the radical the discriminant of the quadratic equation. If this comes out to a negative number, then I'm going to be taking the square root of something negative. So that leads to complex solutions. Let me give you an example. I would like to solve this equation. X squared, let's say, plus x plus, what do I want to make this? Let's make this 25 equals 0. Okay? Now, normally when you look at something like this, you would attempt to solve it using factoring, but you can pretty quickly arrive at the conclusion that this is not factorable. This polynomial is prime. So that's where we jump to our kind of last resort, which is the quadratic formula. So if I use the quadratic formula on this, I have negative b, which is negative 1 plus or minus the square root of b squared, that's 1 squared, minus 4ac, 4 times 1 times 25, all over 2a, 2 times 1. Now simplifying this down, notice I get negative 1 plus or minus the square root. So 1 squared is 1. 4 times 1 times 25 is 100. This becomes 1 minus 100, or negative 99 over 2. Now negative 99, I'm going to do this work off to the side. Because I'm looking at a square root of negative 99, first of all, we have this property of square roots that says we can rewrite that as the square root of negative 1 times the square root of 99. Okay? Now, this is only true, we can only use this property if these are not both negative numbers. We can show that that leads to some crazy contradictions, but if at least one of them is positive, you can always do this. The negative 1 becomes I. And the 99, I could just leave it that way, or I could simplify it. It becomes times 3 root 11. We've simplified radicals before. That's what that one would simplify to. So this could be written as I times 3 root 11. Although oftentimes we sneak the I in there so that it's right next to the radical. So I'm going to write that slightly differently over here. This is equal to negative 1 plus or minus 3I root 11 over 2. That would be the set of solutions to this. The fact that I'm taking square roots and can get negatives means that complex numbers will naturally show up as the solution to a lot of different quadratic equations. But remember this process over here for how to do that. I'm not going to bother trying to do anything else to this. This is as simplified as I'd like to get it. One thing I do want to point out, that I, sometimes people will take the I and put it over here as well so that it looks like A plus or minus BI, the form for a complex number. Me personally, I usually don't like writing the I over here, only because if you're writing really quickly, your square root symbol can stretch a little bit further than you intend it to, and it may look like that I is underneath that radical instead of next to it. That is a completely different number if you put that I under that square root symbol. So to be careful to not make that mistake, I always like to put my I's to the left of radicals instead of to the right. Okay, one more thing I want to look at, and it's using complex numbers in algebraic expressions. So I'm going to do just one example of these. It's fairly straightforward, but you do have a couple of problems that you're going to do like this. So evaluate, let's say, z squared minus 2z plus 3i at z equals, let's say, 1 plus I. Okay? So this is exactly what it sounds like. We're plugging a complex number into a polynomial. And then once we've done that, we use all of the rules that we've already come up with for arithmetic with complex numbers to simplify that down and end up with just a single complex number as a result. So if I were to do that, I'm plugging 1 plus I in for all of the z's here. This becomes 1 plus I squared minus 2 times 1 plus I plus 3i. Okay. 1 plus I, you expand that out and multiply. We actually did this one already in a previous example. When we did this, it came out to 2i after simplifying everything down completely. This, the negative 2, we just distribute in. So I get minus 2 minus 2i. And then this plus 3i, there was no z's in this part of the expression, so this is a constant. That's just plus 3i, nothing changes there. Okay. Finally, I combine any like terms. Notice the 2i and the negative 2i, those are going to cancel. And so that leaves me with negative 2 plus 3i. Fairly straightforward. It's really just using the arithmetic rules that we've already talked about, but kind of in the context of plugging a complex number into a polynomial. So that's all there is to that. And that's going to wrap up this first half of our unit on complex numbers. Like I said, next time we're going to talk about the geometry of complex numbers.